Hi, in this lecture, we will build a machine learning model for predicting the growth of a cancerous tumor. So we will try to predict how big the tumor grows in volume, and if there is an intervention like chemotherapy, how does it shrink, at what rate, and after a given number of days, what could be the predicted size of this tumor. We will try to model this. Of course, we know that cancer is one of the most complex problems to even understand properly, let alone model. So obviously, the model that we are going to be using here will have a lot of assumptions, but the interesting thing that we will incorporate here is we will incorporate a neural network into existing simple cancer tumor growth models to see what is the power of a scientific plus machine learning based models. And this will be coming under the umbrella of scientific machine learning. So let us get into the lecture. So a tumor growth happens in the following way. A random cell in our body can mutate, and it can mutate in such a way that it experiences a rapid rate of growth. So this rapid rate of growth results in accumulation of multiple cells in one location growing as a tumor. So in the early stages of the tumor growth, the rate of growth will be very rapid. The rate at which cells multiply will be very rapid. But later, as the tumor grows in size, the rate of growth can reduce because there will be saturation due to lack of enough nutrient for all those cells in the tumor, because there is only so much nutrient available from the body, right? And just like our normal body cells, cancer cells also need energy to consume, to grow and split. So there will be lack of nutrients, lack of oxygen, and lack of actual physical space in that location for the tumor to grow. So this knowledge which we have as humans can be put into mathematical equations to model the rate of growth of tumor. So a simple model which can basically mathematically express the rate of increase in the size of tumor or rate of increase in the number of cells inside the tumor, etc., is based on this Gompertzian model. So this is named after a famous scientist, Benjamin Gompertz. So Gompertzian model is not specific for cancer tumor growth. It's also a generic model for many other problem statements where initial rate of growth is rapid and later rate of growth is reaching a saturation. So this GIF animation basically shows the splitting of cells and how one cell or like one cancerous cell can lead to another exact replica of that, and then this can increase rapidly, and this one cell lead to ultimately formation of a big tumor. And so this simple ordinary differential equation represents the rate of growth of the tumor in size. It could be the mass, it could be the volume, it could be the number of cells, it can be any parameter of interest. So for simplicity, let's assume that this T is the size of the tumor or volume of the tumor, right? So dt by dt, so here t, small t is time, capital T is the tumor size, is equal to r times tumor size multiplied by natural logarithm of k by t minus c of t, where this t is the time, multiplied by the tumor size. Now this equation may look a bit complicated in the beginning, but I'll split this into very understandable simple terms and I'll explain the logic behind this equation. So first of all, this equation is trying to model rate of change, right? This is not modeling the tumor size itself as a function of time. No, that is not what this equation is doing. This equation is giving us the rate of change of size of tumor at any given point of time. Now, obviously, if we want to find the actual size of tumor at any given point of time, we can integrate this equation. But while integrating, you have to also know the initial condition, right? So we have to know at time t equal to 0, when you are starting your measurement, what is the initial tumor size? So here, capital T represents the size of tumor. It can be a representative of the number of cancerous cells in a tumor. It can be the volume of the tumor in millimeter cube or centimeter cube. It can also be, unitless, like you can normalize whether it's a mass or whether it's a volume or whether it's a number. You can simply normalize it, and that the value of T can be something between 0 to 1. 1 means tumor has reached its maximum possible size. 0 means it has shrunk to basically nothing. Then you have R, this small r term. It is representative of the tumor growth rate. So it's a coefficient that represents how fast the tumor grows, especially when it is small. So actual tumor growth rate is d capital T by dt, but r is a representative of that. So r is a representative, meaning r coefficient associated with this equation here represents how fast the tumor is growing. So higher the r, higher the dt by dt. Now, the units of r could be number of cell divisions per day. So it's that value of r is influenced by the rate of cell division in the tumor. It is also influenced probably by the availability of nutrients in that particular location where the tumor is, or something to do with the blood composition, like amount of oxygen supply, anything like that. So this is up to biologists to determine what the R can look like based on various factors. Now there is another term, K. K is called the carrying capacity. So carrying capacity is in that particular environment of the body where the tumor is forming, what is the maximum possible tumor size that is attainable? So that is capital K. So then you have, so that is this first term RT log K by T. So this RT log K by T is what happens to a tumor when there is no medical intervention happening, when there is no treatment. The tumor will basically keep growing and it will reach a maximum size, and maybe it will spread to other locations of the body, right? But if there is some sort of intervention happening, then there is a factor that plays to reduce the size of the tumor. So that is this C of T multiplied by T term. So let's say C represents chemotherapy as a function of time. Now it could be the strength of chemotherapy. It could be the number of times you inject certain chemicals, whatever it is, right? So C of T can mean anything. It can mean the amount of radiation therapy that you are treated with. It can be chemotherapy, anything. So C of T represents like the medical intervention that is happening in your fight against cancer. And C of T multiplied by T. So the rate of decrease of tumor is proportional to the chemical intervention and proportional to the current tumor size, because the bigger the tumor, the more it can shrink given a chemotherapy. And this term RT log K by T is the rate of growth of tumor. So these are two opposing factors, and the imbalance between these opposing factors determine whether the tumor is shrinking or whether it is growing. So if this dt by dt is positive, it means the tumor is growing. If it is negative, it means the tumor is shrinking, right? Okay. So that is what I mentioned here. C of T is the chemotherapy induced kill rate. So it's any anti-cancer intervention. Now let us take a moment to discuss how valid this particular equation is, right? So you know that actual dynamics of cancer growth is impossible to predict. It's such a complex disease that we humans haven't perfected predicting cancer or forecasting its future look, how it looks in the future if somebody has cancer. So none of this is a fully valid model. This is an overly simplified cancer growth model, tumor growth model. Yet it captures the essence of it in many cases, and it has been validated in many experimental studies as well. So what we are going to do now is we'll see how we can make this model better by incorporating machine learning. We'll also discuss why do we have the need for incorporating machine learning here? Because if you already have a model, what is the need for machine learning, right? So let's discuss that. So this Gompertzian model has some issues. The main issue is what I already mentioned. It's too simple. But let's say we are okay with a simple model because we are not trying to exactly predict the tumor size to the point, but more like we want a model which gives us a rough estimate of how the tumor growth looks like. Then maybe Gompertzian model is fine. But the problem is this, right? We don't know what are these terms, the R, K, C. So R is dependent on the rate of growth of the tumor, and maybe it depends on the particular cell type, the particular cancer type, etc. K is the maximum possible size the tumor can take in that specific environment it is in. So if it is in the pancreas, if it's in the brain, if it's somewhere else in the body, the K value will change. So it's very difficult to estimate also. Even if you know where the tumor is present, it's very difficult to estimate the value of K. Similarly, C of T, it's corresponding to your chemotherapy intervention or any other medical intervention. It might be difficult to mathematically quantify the C of T value. But if your intervention is if you know this is the equation that you are going to use, you can convert whatever your intervention is into a meaningful C of t parameter. So among these three parameters, R and K are very difficult to estimate. C is also difficult, but it is possible to know what the C of t can look like. So now, given this difficulty, what can we do? We can probably incorporate machine learning to make predictions. Predictions of what? Predictions of the future cancer, future tumor size. So in a traditional machine learning method, this is what we do, right? We may have a particular tumor size at initial time point. You may have a cancer intervention rate represented by C naught. Let's say it's a constant. Then you will input these two terms into a neural network. It can be a deep neural network. And then this outputs the size of the tumor after, let's say, 1 month. Now, how does the neural network make this prediction? It can make this prediction by knowing this data. You should have the initial tumor size and the cancer intervention in terms of numbers. You should also have the tumor size measured from many experiments after, let's say, 1 month. For very many different patients. And then if you have large data set like this from maybe different hospitals or maybe different oncology departments, yes, perhaps you can build a very good deep learning model, deep neural network, which can make a prediction that, hey, if this is the initial tumor size and if this is the extent of intervention that you have, then after 1 month, the tumor size predicted is this much. Maybe this model can be accurate to a good extent. But the problem here is you have no idea what is happening inside the model. This is a traditional black box machine learning model. You don't have good interpretability. So there is one more problem, right? The problem is that you already have a decent model. You have the Gompertzian growth model in which some things are sensible. This RT ln k by t is a term which captures the essence that cancer tumor grows fast initially, and then later the growth rate reduces. So initially, let's say when this tumor size is small, then you can approximate dt by dt equal to RT. You can approximate it like this. So so there is a meaning associated with having the RT term and having the ln k by t term. Similarly, there is also a meaning for minus C of t times t term, because if there is a intervention happening, then of course it contributes negatively to the tumor growth. So why should we throw all of this knowledge away by taking a simple, taking a black box machine learning model? Because yes, I agree, we have unknown parameters, but we also have some known parameters and known relationships. So why can't we preserve that somehow? So this is where scientific machine learning enters into picture, where in scientific machine learning, in this problem statement types, what we can do is we can simply replace unknown terms with neural networks. So here, look at the Gompertzian equation, dt by dt equal to some neural network multiplied by t logarithm of some other neural network divided by t minus C of t multiplied by the tumor size. So here I am making one assumption. It is that, since we ourselves are doing the chemotherapy intervention, we know the C of t term. So that is an assumption that I am making. We can take away that assumption also. If that is the case, then you will have one more neural network replacing C of t. So here, with this kind of a model, and I'm going to explain you what I mean by replacing the neural network, because you might be wondering, what does it mean when you have a differential equation plus neural network together? And what do I exactly mean by replacing? What is being replaced? So I can explain that in a moment. But this kind of a system where you have a mix of neural network and ordinary differential equation or any differential equation, it's called as Universal Differential Equations, UDE. It is a very powerful framework within scientific machine learning, where here we are combining the science of tumor growth with the predictive power of machine learning, because machine learning models are so powerful if there is enough data to predict what is going to happen. Like it can do forecasting, it can make predictions for unknown data points. So this is called UDE because we are using a universal function approximator like neural networks here. We are also using differential equations here. So that is why this is called UDE. So here we have a question. So in the UDE for Gompertzian tumor growth model, we have two separate neural networks, right? So the first term, which was R, is now replaced by this NN1 term. The other term, which was K, is now replaced by the NN2 term. So NN1 and NN2 are two different neural networks. So now the question is, what goes into these neural network as inputs? What comes out of it as outputs? So let us discuss that. So neural network 1, NN1, is supposed to predict the parameter R. And for predicting R, it takes one input, T of T. That is the size of tumor at a given point of time. Now, obviously, you might have a question that we are trying to predict the size of the tumor as a function of time. So how do we have this in the first place? So here, remember that you have one thing, which is the initial tumor size, T of 0. So you can use T of 0 as the input into the neural network to make an initial prediction of the tumor size R. Otherwise, you can choose the tumor size in the beginning as random. So T of T as a function of time, you keep it as random numbers as an array. So if you have 10 time points, start with a random tumor size and then try to predict a value of R using neural network. And then what you can do is in the Gompertzian model, you use the predicted value of R here. So this NN1 is nothing but the output from the neural network 1 used to represent the value of R. Is this the actual value of R? No, it is simply the predicted value of R. Similarly, NN2 is used to predict K, and NN2 also uses the tumor size T as the input. So you are having two separate neural networks here, one for predicting R, one for predicting K. And just like NN1, you plug in the value of K here in the place of NN2. And then what you do is now you have a D tumor size by dt equation, right? And this is the UDE predicted rate of change of tumor size. This is not the actual dt by dt. This is predicted by the UDE. So the initial predictions made by the UDE will be very bad, meaning it will be very far away from the actual tumor growth. So now if you use numerical integration to predict the actual size of tumor at another point of time. So you start from the initial time point 0, and let's say you want to make a prediction, the size of tumor, predicted size of tumor. So this cap means it's a predicted value at a time point t plus delta t, that is equal to the initial size of tumor plus dt by dt, that is rate of change of size of tumor predicted by the UDE. And what is that? That is this equation. This equation is the predicted value of rate of change of size of tumor by the UDE multiplied by the delta t. So this is one step of numerical integration, like an Euler integration. Now you can do this for a large number of time steps to get the predicted value of tumor size at, let's say, some other time point ti. So this is what you get after performing numerical integration once you have neural network predictions. Now, please understand, the neural network predictions are not directly enabling you to predict the size of tumor. Rather, the neural network predictions give you these two parameters which allow you to make a prediction on rate of change of tumor size. Now, with this predicted rate of change of tumor size, you make a prediction on the actual tumor size by performing numerical integration. Now, okay, how do we know whether the neural network has made good predictions, meaning how good or how bad the UDE is? For that, you have to compare the predicted value of tumor size with the actual value of tumor size. Now, actual value of tumor size you can know in few different ways. One is if you have experimental data set, you can use that as the actual value of tumor size as a function of time. You can find this experimental data from published papers in the literature. The other option is you take the Gompertzian model by assuming the value of parameters R and K. So you have to take known values of R and K and then solve the differential equation, the same differential equation. And what is that? It is dt by dt equal to R, known value of R, multiplied by T, ln K by T. So this is the tumor growth term, and tumor shrink term is the C of T multiplied by T. So with the known value of R and known value of K, these two terms, you can calculate the actual dt by dt and then numerically integrate this dt by dt to find the actual value of tumor. So this actual value of tumor will be the ground truth. So see here, I have not put the cap because this is the actual tumor size at a given time point. So now once you have the predicted value of t and actual value of t, which are the tumor sizes, you can calculate the mean squared error. So this mean squared error is 1 by n sigma I equal to 1 to n, the predicted value of tumor at time point ti minus actual value of tumor size at time point ti squared. So this difference is the error. The square means you are squaring up the errors, and sigma I equal to 1 to n divided by n means you are taking the mean. So that is why you have three terms: mean of square of errors, mean squared error. Now, this mean squared error is the measure of how good or how bad your UDE framework is. If mean squared error is very high, it means neural network is making very bad predictions of R and T. And because the R and T predictions are very bad, the DT by DT predictions by the UDE is very bad. And because of that, the final result of numerical integration, which is T cap, is also very bad. And that means your mean squared error is very high. So now the singular goal of the training process of this UDE is to minimize this mean squared error. And what would that mean? If mean squared error is minimized, the predictions of R and K by the neural network will enable you to predict good values of rate of change of tumor growth, which means you can perform numerical integration accurately to get a much better estimate of the predicted tumor size at different time points. So now this is the logical construction of UDE for solving this tumor growth problem. Now let us build the UDE. Let us once again define the individual steps. So first we need to know the initial condition T0. So T0 is the size of tumor at the starting point of your noticing. It has to be a finite value. It can't be zero, because if it is zero, that means tumor does not exist. So you can't start with zero. It has to be some finite small value. Then what you can do is to create the ground truth so that you can compare your UDE predictions against the ground truth. You can solve the Gompertzian ODE with a known value of R and known value of K. So this will give you the actual value of tumor size as a function of time. This is the ground truth. And then what you do is you define your UDE where R and K are unknown. And then the goal of this UDE is to have a neural network which predicts R and K. Then that will help you predict dt by dt, and that will help you numerically integrate this dt by dt and calculate the predicted value of t of t. Then you solve the UDE. And what do we mean by solve the UDE? We simply mean that you look at the difference between this predicted and actual value of t, and that will be the mean squared error. Then you perform backpropagation so that the neural network parameters, what are the parameters? That those are the weights and biases of the different. So if the input layer has one node, hidden layer has 2 nodes or 10 nodes or whatever, and output layer has 1 node, then there will be weights and biases, which are the parameters existing between the nodes that are connected in the neural network. Biases will be into one of these nodes, not into all the nodes. And then if you can modify those parameters such that you make better predictions of R and K, you are moving towards a better and better neural network, which means you have a better and better UDE. So this is the whole process of backpropagation and training the neural network. And once you have the fully trained UDE, which means fully trained neural network, you can make good predictions of tumor size, which will match almost closely with the ground truth value of the tumor size. And once you have the trained UDE, what you can also do is an exciting thing. And this is where the UDE approach in SciML gives you the most promise: forecasting for future time points. So how can you predict the size of the tumor? Let's say, given you have a trained UDE for 0 to 30 days, can you forecast the size of this tumor to 50 days or 70 days? Yes, so we can do that. And that is called extrapolation of the results using the trained UDE parameters. So we'll be doing also this today. So now we can get into coding to build the UDE framework. I'll be coding this in Julia, but this same logic is applicable for irrespective of whether you're coding in Julia or Python. The reason why I'm using Julia is because for SciML framework, Julia has the best packages. So now let us first walk you through the code so that you understand every single block in the code. I have already written the code. I have already run it, optimized everything. So it's working very nicely. But before we run the code, I want you to walk line by line through the code so that you understand what's going on. And then I will also walk you through implementation so that you can try the same. And then you can play with the parameters a little bit. So first is importing the required packages so that you can run the code. What I'm going to do is I will run the code initially without importing the packages, so you know which package is used for what, right? So I will for now skip this, and then when I'm running the code, I will show you without importing the package. Then it will cause some error. Then we can fix it one by one by importing the required packages. Now this block of code is for creating the synthetic ground truth data set. Why do I call it a synthetic ground truth data? Because this is not tumor size data obtained from experiments. This is rather obtained from assumed values of R and K put into the Gompertzian growth model. So this is synthetic tumor size data as a function of time. So in the code, we first define the number of days for which we are simulating. So let's say 50 days. And here the tumor size t, it's unitless, meaning I have normalized it such that if the tumor reaches its maximum possible size, it will be 1.0. And if the tumor is minimum, meaning it shrinks to nothing, it will be 0. So the tumor size t can be a value between 0 and 1. So T0 is the initial tumor size, and 0.05 means the tumor has reached 5% of its maximum possible size. So this is where we are starting from. Now we have three parameters for synthetic data generation. So 0.5 is the value, it's the normalized value for R. R is the coefficient corresponding to initial growth rate. 1.0 is the maximum possible tumor size in that given environment, the value of K. And C is the strength of the chemotherapy intervention. So here I have initially put the value 2. We will play with this number 2 actually to see how different strengths of chemotherapy intervention affects the tumor growth, size growth, or tumor size shrinking. Then you say the U0. So U is the parameter which corresponds to the tumor size T, right? So U0 means the initial condition, which is same as T0. Then T span, time span, we are defining from 0.0, which is the starting, to 50.0. Then we say we create a variable called T, which creates a set of numbers from 0.0 to 50.0. Now this function, tumor growth chemo, is a function which helps us solve the ordinary differential equation problem. So here first you see that I have defined T equal to max of u of 1 comma 0. Now what is u of 1? U of 1 is T itself. U of 1 is T, and du of 1 in Julia notation is nothing but dt by dt. Okay. So u of 1, why did I put this max of u of 1 comma 0? Because I want to ensure that negative values of tumor sizes are not coming, because tumor size is a positive number. And in our simulation, it should not happen such that, let's say tumor size became t equal to 0.01, but dt by dt is a big negative number, let's say -2. Then if I run the simulation, it should not happen such that now I'm having a tumor size of minus 1.99 or something. This should not happen. So to ensure that tumor size is always positive, and I cannot take absolute value, then the tumor size will again become a very big tumor if I take the absolute value of this. So then what I do is, if I get a small negative number as the tumor size, I will convert that into 0. But if tumor size is a positive number, I will retain it as such. So that is why you see this max of tumor size comma 0. Then you have the tumor growth rate, maximum tumor size possible chemotherapy intervention. It's actually packaged into this parameter P variable. So we are unpacking it. Then you have the equation which denotes the rate of change of tumor size, du of 1. So this denotes du by dt, which is dt by dt. So that is RT log K by T. So log is already natural logarithm. And here the C of T, which is chemotherapy intervention, C of T, I have written as sigmoid, C times sigmoid of T by 5, right? Yes, T by 5. So now here, the value of C that I have assumed is 2. So let's look at what the sigmoid function looks like. So sigmoid function looks like something like this shape between 0 and 1. So let me show you the sigmoid function. So this is the equation of sigmoid function, s of x equal to 1 by 1 plus e raised to minus x. So for all values of input x from minus infinity to plus infinity, sigmoid will change its value from 0 to 1. So now what does this mean in terms of chemotherapy intervention? What it means is, so if this C is a constant, this C of T equal to this C, maybe I can call this as C naught. If this is a constant whose value is 2, it means your maximum chemotherapy strength is going to be, as a function of time, is going to be 2 only. But you are not going to start the chemotherapy with the strength of 2. You are going to start it from a small number. So let's say your T is starting from 0. Sigmoid of 0 is what? Sigmoid of 0 is half, right? So this is sigmoid of 0, it's half, 0.5. So you are starting with the half strength chemotherapy, which means C is 0 multiplied by 0.5. So sigmoid of 0 will be 0.5. So instead of starting with a chemotherapy strength of 2, you will be starting with a chemotherapy strength of 1. Then as time increases, you will increase the strength, and maximum strength after a long period of time of chemotherapy will be 2. Right? So that is why we are using this chemotherapy function C of t equal to C0 sigmoid t by 5. And where are we defining this C0 in the code? This guy. This is the this third guy in the P0 parameter is the strength, is the final maximum strength of the chemotherapy. Okay, so that is C multiplied by sigmoid of t by 5. Sigmoid is already defined in Julia, the math function sigmoid, and multiplied by t. So now this function is over, right? So we end the function here. Then we define the ordinary differential equation problem using this ODE problem function predefined in Julia. And there we input the function tumor growth chemo, and we input the initial values of initial value of the tumor size. We input the time span for which we are solving. We also input the parameter value p naught. Then we solve this using the fifth order Runge-Kutta. So solver is also defined in Julia. To the solver, we pass the problem that we have defined here. Then we save the values of the solution at time points t, which ranges from 0 days to 50 days. Then we store all of those values in this true solution variable. Then what we do is now we have our ground truth data ready. So the ground truth data we can plot to get the tumor size as a function of time. And this tumor size is in presence of growth plus the shrinkage due to the chemotherapy intervention. So now this plot, whatever plot we get out of this will be the ground truth data. I just want to show you how the plot looks like. So see, this plot I made for some particular value of C, R, and K. And the initial starting size of the tumor is 0.05, meaning it's 5% of its maximum possible size. Then it keeps growing. Chemotherapy is applied, but still it keeps growing to, let's say, 9% of the size or something like that. Then it shrinks suddenly, and then it shrinks to less than 2% of its maximum possible size. And if the chemotherapy intervention is very strong, you can also shrink it close to 0. So which means tumor is non-existent. So this is the ground truth data simulation. So this is a synthetic ground truth data, what you see. We will run the code and plot something very similar, and we can play with the values of C to see the how the tumor size varies as a function of time for different strengths of chemotherapy intervention. Next is setting up the UDE for predicting the tumor growth. So in the UDE, as I mentioned, there are two neural networks, one for predicting the value of R, one for predicting K. So first, we define the random number generator. Random number generator helps us define the initial weights and bias parameters of the neural network as random numbers. So R and G is the random number generator. Then you have two neural network. First neural network is called as N and R, this guy. Second neural network is N and K. So N and R has one input and one output. So it's having one input node in the input layer. Then you have 10 nodes in the hidden layer. Then you have one node in the output layer. So that is 1, 10, ReLU. ReLU for rectified linear unit. So rectified linear unit is the activation function that is being used at the exit of this hidden layer here. So ReLU, then ReLU, then ReLU, like that. There are 10 nodes, and then they go into the output. And then from, so this is like a fully connected neural network. This node is connected to every single node in the hidden layer, and then connected to every single node in the output layer. So even if you had two nodes in the input, if this neural network required two inputs, then you can put 2, 10, then both the nodes in the input layer will be connected to all the 10 nodes in the hidden layer. So this is called as a fully connected neural network. So here we are using this lux.chain because you are chaining the multiple layers of the neural network sequentially. So you are constructing the layers connection from input to hidden, then you are making the connection from hidden to output. Similarly, you have exactly same structured neural network, but separate neural network for predicting K, right? So that is NNR and NNK. Then you have the neural network initial parameters P1, P2 for the neural network 1 and 2. ST1 and ST2 are the states of the neural network, which allows you for batch processing of the data. So in generating the P1, P2, ST1, ST2, you pass the random number generator as well as the neural network architecture into the lux.setup function. Then you create a P0 vector, which is like a tuple, which stores the value of the initial parameters of neural network 1 and neural network 2. And then you convert that into a component array format. You will see where this P0 vector is passed so that you can have the initial parameters of the neural network initialized using this random number generator R and G. Now, forget this soft plus my soft plus function for a moment. I'll explain what that is. So first, let us look at this Tumor UDE function. It has the exact same format as that of the Gompertzian model function. Du is for passing the rate of change of tumor growth. U holds the tumor growth itself. P is the parameters, which are R, K, and C, and T is the time. So now here again, we define T equal to max of U of 1, 0. So if the tumor growth, which is U of 1, tumor size, which is U of 1, if that is greater than 0, we will pick that. If it is less than 0, we'll convert that into 0 itself, because we don't want negative tumor sizes. Then we say the R output is equal to the output you get from the neural network 1. And into this neural network, we are simply passing one input, which is the current tumor size T. And then you have P dot layer R, meaning the P dot layer R is this. P dot layer R will give you the P1 parameters, initial parameters for the neural network 1. And ST1 is the states of the first neural network. Similarly, and this underscore means this neural network is giving you two outputs. One is the state and one is the output value R, but you are ignoring, you don't want to store the state. So that is why you have given R output comma underscore, which means you are not storing both the outputs. You are only storing the R output given by the neural network into this variable. Similarly, N and K is used for predicting the value of K. So first you pass the value of T, the tumor size. Then you pass the value of the initial layer parameters. Then you pass the state, and then this neural network will give you two outputs. You are only storing the K from that output. Then you do one thing. Here you say R equal to clamp my soft plus R out of 1. So you are clamping the value of R between 10 to the minus 4 and 2. Actually, you know what? This 2, instead of 2, we should clamp it maybe between 1.0. 10 to the minus 4 and 1.0, because we are saying the rate of growth of tumor is a number between 0 and 1. Similarly, K is the maximum possible size of the tumor. We can also say that this is a number between 0.01 and 1.0. This number can be actually small, but this number, let's keep it below 1, because we are normalizing the size of the tumor. Then here we have the equation that calculates the rate of change of tumor size. So du1 is the derivative of u of 1. U of 1 is tumor size. Du of 1 is dt by d time, equal to rt log k by t minus p0 of 3. So p0 of 3 is what? P0 of 3 is this guy. So P0 has three numbers, the value of R, value of K, and value of C. Here, value of R and K we can't use in the UDE because that is what we are trying to predict. We use the value of R and K here only for generating the synthetic ground truth data. But the value of C, we are saying that we know the value of C, the chemotherapy intervention. So P0 of 3 is nothing but 2. The value of that is 2. And then multiplied by sigmoid of t by 5 multiplied by t. So this is the value of C. So in the previous function, we were using C times sigmoid of t by 5 over here. So same thing. Okay. And now, once the function is ended, you define the similar to how you define the ODE problem, you define the UDE problem, where you use the same function ODE problem, but you pass the tumor UDE function this time, this function, and then you pass the initial tumor size U0, you pass the time span, and you pass the P0 vector. So this P0 vector stores the initial parameters, the layer parameters of both neural networks. Then you define the loss function. Loss function is a mean squared error loss, right? So for getting the loss function, you need to know the actual value of tumor size and the UDE predicted value of tumor size. So UDE predicted value of tumor size is obtained by solving the UDE problem defined above. So this is the UDE problem definition, and this is the solution. So you are calling the solver with UDE problem as the problem and fifth order Runge-Kutta. So this T-SIT5 is nothing but a fifth order Runge-Kutta. It's called Thesaurus Runge-Kutta fifth order solver. It's used in Julia. And then you are passing the initial tumor size, you are passing the parameter, which is R, C, R, K, and C. R and K you are not using, only C you will be using. And you are saving at time points, all the time points used in your time, which is from 0 to 50 days. And this is an additional parameter, but let's not go into the details of this parameter. Then here what we are saying is, if any of the parameters after solving is like a big number, then we'll convert the loss into infinity. So we will return the loss to be infinity, because if, so is nan means is NaN. So this you might be familiar. NaN means not a number. So this especially happens when division by 0, etc. happens. So if you try to attempt 5 by 0, most programming languages will give you something like this, NaN. So is NaN, this guy is checking whether there is a not a number anywhere in your solution. If that exists, then what you're saying is, okay, then your loss should be infinity, because whatever you have done in your UDE to solve this problem, it has resulted in not a number, which means your loss should be very, very high. Otherwise, you simply provide the mean squared error as the loss. So this is the mean squared error. So then you return it. So that is the definition of the loss function. And then you train the neural network using this particular optimizer, LBFGS. So BFGS is like the name of 4 people who came up with this algorithm. And here, what you do is you try to minimize the mean squared error. So first you say your optimization function is the loss function itself. Where is this loss function defined? Here. This is the loss function itself. And then you say optimization problem that you are looking at is to optimize this opt function guy. And you are using this optimization problem function, which is inbuilt in Julia. Then you want to get the UDE trained parameters. What are those? The final values of predicted R predicted, and K predicted. So you are interested primarily in these 2 guys. So for that, you solve this opt problem using optimization optim.jl, optimjl.lbfgs. So this is the solver, right? So here you have actually few different options. You could use vanilla gradient descent. You could use stochastic gradient descent. You can use momentum-based gradient descent. You could use root mean square propagation, or you could use Adam optimizer. So there are many options for optimizers here. So the reason why I chose LBFGS was because I was initially using Adam and I was not getting convergence for some reason. And then I was playing with the optimizer a little bit, and I noticed that LBFGS was giving me actually convergence. But I'll be very happy to see if any of you get the convergence using Adam optimizer itself, because Adam is very famous. And max iterations you can play with. So we'll start with initially maybe 2 iterations, and then we'll go up to 20 or 50 iterations max. It's like epochs. How many number of times are you training to minimize the mean squared error? Then we can plot the final solution. So the trained solution is nothing but the trained values of R and K. So we are solving the UDE problem using the trained parameters. So what this means is, if you have a ground truth, actually I have it here itself. So here this ground truth is the red color graph. The blue dotted graph is the trained UDE tumor size. So after training, what is the UDE also predicting? And here you can see that the ground truth and UDE prediction are matching pretty well. So we'll generate this graph, but I managed to get this graph after I think 20 iterations, not 2 iterations, but we'll run initially starting with 2 iterations. Then you will see that the prediction is a little bit off from the reality, something like this. It may predict something like this. And then as you increase the training epochs, you will make better and better predictions. But is that enough? No, that is not enough. You also have to make forecast. Because here your training data is from 0 to 50 days. But let's say you had only 0 to 25 days as the training data. You have to make a forecast for future time points. So we'll do that also in the last part of the code. Here we'll forecast beyond our original training data point. So if 0 to 50 was the initial training, we'll try to forecast beyond 50 till 100 days. So again, plotting that part is very easy. So we define the new time span using 100 as the maximum number of days. And using the new time span and using the UDE solved parameters R and K, we again get a new set of predictions, and then we simply plot it. So that is what you see here. So here if the UDE is making a prediction till this point, till 50, UDE is making prediction on trained data. So this was part of training. Now, in machine learning, you will hear something like testing or validation, right? So this is like validation, because your actual ground truth from 50 to 100 days was never exposed to the neural network. So here, actually, the neural network is making a forecast based on what it has found so far. Now, you may wonder like, oh, isn't this an easy forecast to make because it has already plateaued? So maybe this is an easy forecast to make. If you have that doubt, what we will also do is we'll train only from like 0 to maybe 10 days. So the peak is not even covered. Then you will see that this neural network can actually also predict where the peak occurs. So it's amazing, right? So let's actually implement this in code and then play with some of these numbers to see the power of universal differential equation in training very well on these scientific problem statements and also making very good forecasts. So here I have opened Jupyter Notebook with Julia as the kernel. So I'm using Julia 1.10.9. So now let's go to the starting point of the code and let's run it block by block. So as I mentioned earlier, I'll not be importing the packages. We can import it as and when issues occur. So you know what is used where. So first I'm going to simulate the ground truth data. Here itself, there will be an issue most likely because we are not, okay, ODE problem is not defined. So what we can do is using differential equations.jl. So that is one package which we will need. Most likely plots also we will need. Okay, actually that we are using here, using plots. So now hopefully this may work. Let's see. And meanwhile, while this is running, I'm also going to copy the next block of code for UDE model for tumor growth. So this usually gets executed very fast. It's because I'm connecting this Jupyter Notebook for the first time to its kernel. So that's the reason why it's showing busy for some time now, 2-3 seconds. Usually it should not take more than 2 seconds. Then here we changed the R value clamping, right? So this was 2.0 and 2.0 earlier. Now I changed it to 1.0. Okay, here there is one more issue that has occurred. Sigmoid is not defined. And sigmoid must be defined in, maybe let's use JLD. I'm also not sure which exact package uses sigmoid. We'll see. So Lux. So this was the package that was needed, differential equation flux. So now you can see the synthetic tumor growth data, which I obtained by using 1.0 as the value of K, 0.5 for R, and 2 for C. We can play with this parameter, right? So let's keep C as 2 and maybe number of days as 10. You will see that the graph shape changed. So now we are only simulating for 10 days and the tumor reaches a peak size at 5th day. And if C is not there, so let's say C is 0, then tumor will be able to grow to its maximum size 1.0. So I'm now simulating without C, so no cancer intervention, chemotherapy intervention, and you are simulating for 50 days and see the growth. So tumor has reached its maximum possible size in around 15 days. So this is what happens if no medical intervention is there. But if C is there, let's say 0.5, then maximum size, it reached a maximum size of 0.5 or something. And then it started decreasing and it reached an equilibrium low value. And now the stronger and stronger this maximum chemo strength becomes, the smaller and smaller the cancer grows. So here initial starting size was 5%. It grew to around 8% size and then it shrunk to less than 2% size. So this is basically the dynamics of how the tumor grows or shrinks. And if it can be shrunk to 0 size, which can be possible, I guess, if we increase the value of C. Yeah, see here, the maximum chemo strength is 5. So it will go as a sigmoid function from around 2.5 to 5 because we are simulating sigmoid of T by 5, right? So it will never approach exactly 5, but it will asymptotically approach that. And here you can see that the tumor initially was 5% in size compared to its maximum possible size. And then it immediately started shrinking and it shrunk to almost 0. So here, with this kind of a chemo strength, you can basically stop the chemo maybe after, let's say, 15 days, because tumor is non-existent after 15 days. Its size is 0. So if everything is fine, you can stop the chemo, and then if it re-emerges, restarting the chemo. Of course, I'm no cancer expert, but I'm just talking in terms of the model that we have here in front of us. Okay, so now let us go back to the value of C equal to 2, right? This sounds better. And now this is our ground truth data. So we will use this curve as the ground truth data. So we are simulating from 0 to 50 days, correct? Okay, so now let us define the UDE. So UDE is now, okay, random is not defined. So here what we can do is we can using random. So component array is not defined. So that is part of this library called component arrays. So you have to put an S also. Then hopefully it should run. So now UDE definition is fine. And here it is printing the initial size. U0 is the initial size of tumor with respect to its maximum possible size. Okay. Now we can call the loss function. I mean, we can define the loss function, which is here. So loss function is the mean squared error function. And nothing will happen because you are just defining. Now you are performing the training here, and let's only keep 2 iterations. I don't want 10 iterations right now. So 2 iterations. Optimization is not defined. So let's say using optimization. JL is not defined. So I'll add that also. And maybe I'll have to also add lux because that is also not there. So mostly now an error might happen. Let's see. I don't think I added lux anywhere. Yeah. So we'll see if there is no error, then we know that lux is not needed for this code. And meanwhile, let me also copy paste the code for plotting. So this is for plotting the trained value prediction by the UDE. So whatever UDE training resulted in, that we will plot on top of the ground truth data. So while this code is running, let me also explain one small thing which I forgot to explain. That was this mySoft plus function. So this mySoft plus function ensures that you are having almost like a, so this 1 plus exponent of x, right? So, and look at where this mySoft plus function is being called. It is called at, it is called with the R value that is predicted and the K value that is predicted as the input. So what this ensures is, it ensures that the R and K, this is equivalent to ReLU. So log of 1 plus exponent of x is like a more differentiable version of ReLU of x. And ReLU of x, you know, it's not differentiable at x equal to 0. So ReLU of x shape is like this, but this guy is differentiable. So this mySoft plus is used to make sure that the values that you get here predicted by the neural network are more stable, so you can get more stable output. When I did not have this function mySoft plus in the beginning, I was having trouble getting convergence. So then initially I did not even have this upper and lower limits. So then my predicted values of R and K were inducing instability in my prediction. Then I clamped it such that it's the value of predicted R and predicted K is always between these two numbers. Then I was getting better prediction, but still I was having issues with convergence. And then I added this mySoft plus and it was working. I don't know if it is because of the way my initial parameters are initialized using the random number generator. Maybe it is, maybe it is not. I ran it a few times, but I was still facing issues. So that's the reason why I'm using the mySoft plus function. I highly recommend you to also, remove this part and then remove this mySoft plus here. Don't use mySoft plus, just use clamp and see what you get. Maybe it will still work. So we could also try that actually. But anyways, you have the output here with warning. So I'm going to conveniently ignore some of these warnings as long as I'm getting the output. So now we can try plotting. Yeah, so see, now this is the plot. So the red color graph is the true tumor size and blue is what the UDE has learned to predict. So training data still involves 0 to 50 days. And you can see that clearly the UDE is not really trained well. Maybe it's because the number of iterations are very small. It's only 2. So let's keep it 5 and see what happens, right? The prediction improves or not. So this will take slightly more, maybe few more seconds to execute. See, now the prediction has improved considerably, at least better than the previous case. So now we can do, maybe instead of predicting for instead of iterating only 5 times, let us iterate over 20 iteration, and let us run this once again. And hopefully this time your prediction will be significantly better with a almost overlapping kind of prediction. It's not even prediction, it's just training. So for 20 iterations, this is what you have. Fairly good, right? So your training data and your true ground truth is actually matching. Now we can do one more thing here. Instead of using 50 days, maybe I can use, so here, where is the peak? The peak is at maybe 5 days, right? So I can reduce the chemotherapy strength perhaps. So let us say this is 1, and it means now the peak is at 5, right? Then what we can do is, instead of 50 days, I can just simulate for 5 days. So we would not have reached the peak, and peak is something that the neural network should be able to forecast later. So now I'm simulating only for 5 days, and let's see what the prediction of training prediction of the UDE is. If it is good, we can try a bit of forecasting. See, okay, so now UDE is making a decent prediction compared to what the ground truth is. Now what we are going to do is, we will perform forecasting. So for forecasting, what we can do is, we can copy paste the extrapolation code. So this is the extrapolation code. And what we can do is, we can extrapolate from 5 days till perhaps 30 days. And I guess that's it. We can just run the code and see. Now it's able to forecast and see the actual peak in the ground truth was where. If I had written here 20 days, you would have seen the actual peak to be at around 5 days, right? 5 or 6 days, something like that. That is where the peak is. And by 20th day, this is coming down to slightly below 0.15. Now let us see what the UDE has forecasted. The peak is at around 5 or 6 days. So this is correct. And here it has actually come down a little bit more. So basically, UDE is overestimating the shrinkage of tumor a little bit here, because in the actual ground truth, if we were to simulate, it's at 0.145 or something like that. Whereas UDE is saying the size after these many days will be 0.13, something like that. So UDE is a little bit underestimating the size or overestimating the shrinkage, one of them. But still, this is a very good forecast, because in the training data, if you were to consider that this whole thing is your data set, you have data from 0 to 20 days. But we have only used how many days for training? We have only used 0 to 5 days for training. Oh, this is actually 30, not 20. Okay, my bad. So this should be 20. Maybe then the prediction will be better. 1 second. So this should be 5, right? And yeah, maybe now I will see that the prediction is very good. So this should be 20. And now hopefully the final, after 20 days, the tumor size will be slightly less than 0.15. Yeah, see. So now here, the point that I wanted to make was, the percentage of data that is used for training is only 25%, because you have 20 days worth of data. Okay. But you have only used till day 5 for your training. So you have only used 25% of the data, 1/4 of the data. The remaining 75% is actual forecast. It's like validation of your neural network. Imagine any neural network. Do you think you will be able to, if it's a black box model, do you think it will be able to train and validate perfectly with just 25% for training and 75% for validation? It won't happen. You usually use the reverse. You use 75% for training and 25% for validation. Here we are doing the reverse and still getting very good result. And how do we know it's still very good result? We can simply change this to 20 and run and see the ground truth. So this is the ground truth. The peak is at around 5 or 6 days, and here it is slightly below 0.15. Almost exact shape we were able to get here. Peak is maybe at 5 or 6 or even 7 days. Peak is slightly shifted, and here we have slightly below 0.15. And this can be made even better. Okay, how? By maybe increasing the number of iterations. So here we can make it 50, and if this is 50, we will get something even better. Actually, the time should be 5 here. So let me convert this into 5. And now we can see the final result. Hopefully, our prediction would be even better now, because we are now running for 50 iterations. Yeah, so now this is the final plot. You see, it's almost exactly same as what we have here in the ground truth. If we were to put n equal to 20, this is the shape. This is the ground truth, and pretty much this shape is what we have been able to attain. I can take a screenshot here, and I can show you side by side. So let me open this. So this is our screenshot, the ground truth. And this is our UDE prediction. Pretty much the same, right? The shape is very, very, very much the same. So this is really mind blowing, and we have in fact even submitted a paper recently based on cancer tumor growth prediction using universal differential equation, and it has been successfully accepted. The work has been done by one of our students who is part of our scientific machine learning program, but the work is now accepted to the Julia Con happening soon in another 2 or 3 months in the US. So it's an amazing field. Actually, there are a lot of interesting problem statements in which you can combine the ability of scientific models and machine learning to make better predictions than simplified scientific models or black box machine learning models. So this is just a glimpse of what scientific machine learning can do. The possibilities are endless, literally endless. This field has applications in almost any field you can imagine. So with that, I hope you are getting to appreciate scientific machine learning better with this video which you watched. With that, let us wind up the lecture, and thank you so much for listening. We will meet again in another lecture. Try the code out. I'll share the code in the description. So try that out, and let's meet again in another lecture. Take care until then. Bye.